Hello, my dear students. This is the part 3rd of lecture 1 on real analysis second with course code MMPC 202. So, as already we have seen that this A minus union I runs from 1 to k plus 1 AI is equal to A minus union I runs from 1 to k AI minus ak plus 1. Now, since the result is true for n equal to k, so that means this difference can be written as finite disjoint union of members of S. So that's we can write it as B1 union B2 union so on up to union Bm, then minus ak plus 1. These Bi's, they are the members of S and they are also pairwise disjoint. And this follows by inductive hypothesis. So next we can write it as B1 minus ak plus 1 union B2 minus ak plus 1 union so on up to union Bm minus ak plus 1. Again, the set difference of two members of S can be written as finite disjoint union of members of S. So therefore, we have it's equal to B11 union B12 union so on union B1n1. That's the first part of this union. It's equal to. And the second part again, these are the members of S, B2 as well as ak plus 1. So hence can be written as a finite disjoint union of members of S. So we have B21 union B22 so on up to union B2 and 2. This set difference is equal to that union. And so on up to we have the mth set difference Bm minus ak plus 1. Again these are members of S, Bm as well as ak plus 1. So can be written as finite disjoint union of members of S. So hence this union A minus this difference A minus union I runs from 1 to k plus 1 AI, it can be written as the finite union of members of S. And this union, it's they are pairwise disjoint. The members of this union are pairwise disjoint. Members of this union, they are also pairwise disjoint. And members of the mth union, they are also pairwise disjoint. And again, these B1, B2, Bm, they are also pairwise disjoint. Therefore, all the members of this union are pairwise disjoint. That is this A minus union I runs from 1 to k plus 1 AI can be written as finite disjoint union of members of S. So this is that union where these Bij's, they are the members of S and they are also pairwise disjoint. So hence part 1 of third one follows. So now we prove part 2 of this theorem. So part 2 is if A is equal to union A and n runs from 1 to infinity, where A and is they are all members of S, then we show that then this A is a sigma set. And as we know by definition, by sigma set we mean that if this set can be written as finite disjoint union of members of S. Here A is the union of members of S, but they are not disjoint. So in this part we must have to construct a new sequence of members of S. So that sequence must be pairwise disjoint, and the union of the union of the members of that sequence must be equal to union n runs from 1 to infinity an. So if we do that, that means then we are done, because in that case A is a sigma set. That's what we have to put actually as a sigma set. So how do we do that? We construct a new sequence. So let's construct that sequence. So take B1 is equal to A1, same as A1, and take B2 is equal to A2 minus A1. So these B1 and B2, they are disjoint. A1 and A2 may not be disjoint. So the situation is like this. Suppose this is set A1, this is set A2, it's A1, it's A2, that's the intersection portion. So they are not disjoint in general. But B1 and B2, they are disjoint. How they are disjoint? B1 is whole A1 and B2 is A2 minus A1. A2 minus A1. We have to remove the portion of A1 from A2. So it's B1 and B2 is this one, this portion. So this is B1. This is your B1 and that's B2. So clearly B1 and B2 they are disjoint. And so on, we continue this process. We define B3 is equal to A3 minus A1 union A2. So you can easily verify that B1, B2, B3 they are also pairwise disjoint. And in general we define Bn plus 1 which is equal to An plus 1 minus union I runs from 1 to n. So thus we have constructed a new sequence Bn having the following properties. These Bn's they are pairwise disjoint, and one thing more that this union Bn n runs from 1 to infinity, it is same as union An runs from 1 to infinity. As in the case of n equal to 2, here A1 union A2 is same as B1 union B2. So this union is same and this is equal to A. So thus A can be written as disjoint union of sets since Bn is a disjoint. Now, but we have to show that A is the disjoint union of members of S. Not only the disjoint union, but these sets must be the members of S. So we have here BA is equal to union n runs from 1 to infinity Bn, and it's equal to union n runs from 1 to infinity. What's Bn? Bn is An plus 1 minus union I runs from 1 to n Ai. Now look at this difference. So this difference is very important. We apply part 1 of this theorem. Here n plus 1, it's a member of S. And these A1, A2 up to An, they are also the members of S. Therefore, by part 1 of this theorem, we can express this as a finite disjoint union of members of S. So it's equal to union n runs from 1 to infinity, and this difference can be written as finite disjoint union of members of S. So we can write it as it is like this: Bn plus 1 comma 1 union Bn plus 2 comma 2 union so on union Bn plus 1 comma, let me write here the last term, it's say n, say let's write m n plus 2, m n plus 2, and they are disjoint by previous theorem. They are disjoint by previous theorem, and you can easily verify that they are all of them, they are pairwise disjoint. Bn plus 1 comma 1 is disjoint from Bn plus 2 comma 2. But if we express this union, if we expand this union here, it's actually n runs from 1 to infinity. So let's do that. So to make it more clear, it's equal to, if I expand this union, it's n is 1, B2 1 union B3 1 union. So this is the first one. Then second, I apply this union on second term now. It's union. So let's apply it here. It's equal to now n is equal to 1 to infinity. It's b here 1 plus 2, that's 3. B3 to union B4 to union, so up to infinity. And continue this union. It's equal to at this loss stage at so n plus 2th stage. In fact, it's equal to n is 1 first. It's b, n is 1 plus 2 is 3. Here again, it's b n plus 1, b, it's everywhere, this is n plus 1 here, it's 2, just 2 here, B2, 2. So it's B2 comma M, it's here 1, sorry, it's 1 here, B2 comma M2 union B3 comma M3 union, so on, it's up to infinity. So one can easily verify that they are actually pairwise disjoint. All the sets are pairwise disjoint. So therefore, this A, which is equal to countable union of disjoint members of S. So thus A can be written as countable disjoint union of members of S. So hence A is a sigma set. Hence A is a sigma set. So this part research says that whenever A is a union of countable union of members of S, then we can always express A as a countable disjoint union of members of S. So now we have a last part of this theorem which says that the countable union of sigma sets is again a sigma set, and this finite intersection of sigma sets is again a sigma set. First we check this countable union of sigma sets is again a sigma set. Proof first this. So how do we do it? We take any countable class of sigma sets. Sigma sets, each the set is sigma set. So let's take that A and B sequence of sigma sets. We show that union AN is also a sigma set. Each A1, A2, up, so on up to infinity, it's a countable class of sigma sets. We show that the union of this countable class is again a sigma set. So this is a countable class, and since A1 is a sigma set, so we have, because A1, A2, AN, they are all sigma sets, so A1 can be written as a countable disjoint union of members of S, so that means A1 can be written as B11 union B12, so on up to infinity, or we can write it as union B1J, J runs from 1 to infinity. And similarly, A2 can be written as union B2J, J runs from 1 to infinity, and so on. In general, AN can be written as union BNJ, J runs from 1 to infinity, where these BIJs, they are the members of S. And B1Js, they are pairwise disjoint, B2Js, they are also pairwise disjoint, BNJs, they are also pairwise disjoint. In general, BIJs are not pairwise disjoint. So now we have a new class. So consider this class. Consider the class. On this class, it's B1J comma B2J. In general, it's like this: B J, where I comma J runs from 1 to infinity. So these are the members of, they are the members of S. So these BIGs, they are members of S. And one more thing is that it's a countable class, because I runs from 1 to infinity, j runs, it's a countable class. So therefore we can enumerate it. And one more thing is that then this A, and let's write it as A which is equal to union and runs from 1 to infinity. We have to show that this A, which is a countable union of sigma sets, it's a sigma set. So we show that this A is a sigma set. It's equal to, you can easily verify that, it's equal to the double union Bij. I runs from 1 to infinity, j runs from 1 to infinity. Now since this class is countable, so therefore we can enumerate the elements of this class. It's a countable class. So since Bij's are countable, so therefore we can write this Bij where I comma j greater or equal to 1 equal to Cn where n is greater or equal. We can enumerate these numbers as it's a countable class. And now you can write, as I said, A as A which is equal to double union I runs from 1 to infinity, j runs from 1 to infinity, Bij is same as union C, and n runs from 1 to infinity, where C and they are actually Bij's. It's just the enumeration of this class. So these C and they are the members of S. So again, now by part 2 of this theorem, whenever a set A is equal to countable union of members of S, then such a set is always a sigma set. So therefore, by part 2, A is a sigma set. So this proves this part. Now we show that the finite intersection of sigma sets is a sigma set. So it's again the third part. We have two parts of this third part. First part, it was the countable union of sigma sets is a sigma set, and second part is the finite intersection of sigma sets is again a sigma set. So to make it simple, I take two sigma sets, and I will show that the intersection of these two sigma sets is again a sigma set. So let A1 and A2 be two sigma sets. We show that A1 intersection A2 is also a sigma set. Is also a sigma set. Is also a sigma set. So since A1 is a sigma set, since A1 and A2 are both sigma sets, are both sigma sets. So therefore, A1 can be written as countable union of countable and disjoint union of members of S. So A1 can be written as, say, it's equal to B1. It's equal to like this. It's a union B and n runs from 1 to infinity, where Bn's are members of S and they are also disjoint. B intersection Bj is phi I not equal to J. And A2 is also a sigma set, therefore A2 can be written as union say Cn, n runs from 1 to infinity, and these Cn's, they are members of S and they are also pairwise disjoint. For I not equal to J. So A1 and A2 they are sigma sets, so we can write these sets as so now we check the intersection. What's A1 intersection A2? A1 intersection A2, it's equal to union n runs from 1 to infinity Bn intersection union n runs from 1 to infinity Cn, and you can write it as union n runs from 1 to infinity Cn intersection Bn. And this Cn, it's a member of S, Bn is a member of S, and S is closed with respect to intersection, finite intersection. Therefore, Cn intersection Bn is also a member of S. So thus A1 intersection A2 can be written as a countable union of members of S. So hence this is hence A1 intersection A2 is a sigma set. Why it is sigma set? Because this Cn intersection Bn because this I will write it as here. I will write the reason here because Cn intersection Bn, they are all members of S. So this proves the part third of theorem 1. Now next we have a lemma which follows from this theorem actually. So what's that for lemma? Lemma 2. So, lemma. It states that if An is a sequence of sets, is a sequence of sets. An is a sequence of sets in a Semiring S. In a Semiring S, then there exists a disjoint sequence. Then there exists a disjoint sequence Cn such that union An is same as union Cn, n runs from 1 to infinity. And one more thing, and for all n greater or equal to 1, there exists k greater or equal to 1 such that Cn is subset of Ak. So this is actually very simple. We already done it in part 2 of previous theorem. How can we express any union of members of S as a disjoint union of members of S? And second condition, that's again simple because in the part 2 of the theorem, theorem 1, we have constructed a new sequence Cn from N like that. We have defined it here. Suppose we have a sequence An in S, which is not disjoint. Then we define a new sequence Cn by following. We define C1 equal to A1, C2 equal to A2 minus A1, and so on up to Cn plus 1 is equal to An plus 1 minus union I runs from 1 to n Ai. Then they are pairwise disjoint, this sequence Cn, and the union An is same as union Cn. But we have to show that this sequence is disjoint, and it should be from our Semiring S. And here these they are not the members of S. They are disjoint but not members of S. So how can we do that? Again, this n plus 1, it's n plus 1 minus the union I runs from 1 to n. So by part 1 of theorem 1, this difference can be written as finite disjoint union of members of S. So therefore it can be written as union Cn means an minus that. So it can be written as finite disjoint union of members of S. So we can write this Cn as Cn. Let's write it as Bn1 union Bn2 up to infinity. It's not infinity, it's finite because it is a finite disjoint union. It's union Bn 1 n2 so on n. So let's write here Bn1 Bn2 say Bn. Okay, it is okay. Bn. So I should write C1 as Bn1. So let's write here Bn and 1, Bn and 2, so on up to Bn and n. Okay. N runs from 1 to infinity. So now these numbers, this union, okay, this, so we have a union A and n runs from 1 to infinity is same as union C, and n runs from 1 to infinity it is same as union this n runs from 1 to infinity. Then here it's B and n1 union B and n2 union B and n. So this it's the countable union now. Now these are the members of S. It's equal to, if I can expand this union, it's B1 1 1. Here I apply the union on this set. Union B2 to 1. So up to infinity. Then union, it's now apply the union here. It's equal to B1 1 2 union B2 2 2 union, and continue this process. So m times its union B and equal to 1. It's 1 1 m union B 2 2 m and equal to and this gives union An is equal to union n runs from 1 to infinity Dn, where Dn is a pairwise disjoint such that for all n greater or equal to 1 there is k such that Dn is subtract k. So this completes the proof of. So this is the end of the lecture 1.